Welcome to this first lesson of the specialization on high performance and embedded computer architecture. My name is Ben Julink and it's my honor to be the instructor of this course. The purpose of this lesson is to give you a definition of computer architecture and to present the high-level objectives of this specialization. Every day we use many computers without really thinking about them. Computers really have changed the world. I can give many examples of this, but in the interest of time, I will give only one. The announcements of the new Pope in 2005 and 2013. This picture here shows a photo of St. Peter's Square during the announcement of Pope Benedict in 2005. As you can see, at that time there were not many cell phones. There's a person here on the right who's taking a picture, and there's a person on the left who seems to be reading a text message. This picture, on the other hand, was taken from the same viewpoint during the announcement of Pope Francis in 2013. Now everybody is using a cell phone, and the person here in the middle is carrying a tablet computer. Each and every cell phone contains a small computer, a small processor, and the architecture and organization of such computers is the topic of this specialization. Let's start with defining what computer architecture is. This is a definition that used to be on the www Computer Architecture webpage and that also used to be on my homepage. Computer architecture is the science and art of selecting and interconnecting hardware components to create computers that meet functional, performance and cost goals. So computer architecture is not only a science, but also an art, implying that imaginative or technical skills are involved. Furthermore, it's about selecting the most appropriate hardware components and connecting them in the best way to build computers that can deliver a certain functionality with the highest performance and with the lowest cost possible. Computer architecture has nothing to do with using computers to design buildings. Publishers often send me building architecture books, but these publishers don't really understand my profession. This is a picture of the world's first electronic general-purpose computer, the ENIAC, designed by John Markley and J. Presper Eckert of the University of Pennsylvania. Its construction started in 1943 and it was announced in 1946. We have come a long way since then. Let me now present the objectives for this specialization. The objective of the first course, Fundamentals, is to review performance, processor instructions, pipelining and the basics of caches. For example, this figure illustrates Amdahl's law. It shows the speed up as a function of the number of processors for different parallel fractions. There are not many equations in computer architecture, but this is one equation that you should know by heart. This shows a snippet of MIPS64 assembly code. After the first course, you will be able to program and optimize MIPS64 assembly program. This figure illustrates the canonical 5-stage pipeline consisting of the stages instruction fetch, instruction decode, execute, memory access and write back. I will review this pipeline organization as well as the challenges it has and how they can be solved. Finally, this figure shows the organization of a two-way set associative cache. In the first course, I will review the basics of caches so that you will be able to, for example, compute the number of cache hits and cache misses given a sequence of memory references and a certain cache organization. In fact, I assume that you will know most of these topics, since they are typically covered in introductory computer architecture courses. But since my students come from everywhere, they do not always have the same background. Therefore, the main objective of the first course is to align these different backgrounds. One of the objectives of the second course is to explain how instruction-level parallelism is dynamically exploited in modern processes. Here I will discuss topics such as out-of-order execution, register renaming, branch prediction, speculation, etc. To give you a preview of these topics, This figure shows a block diagram of Intel Nehalem's microarchitecture, which was the organization of the first Core i7 and Core i5 processors. Unfortunately, this slide is too small to clearly see all the components. Therefore, I will highlight some blocks. This block, called reservation stations, is needed for out-of-order execution. Out-of-order execution means that instructions are executed in an order different from the normal program order. In modern processors, instructions are executed as soon as their operands are available and a functional unit that can execute the instruction is free. The Nehalem microarchitecture has 6 functional units. It can execute 6 instructions in parallel. This block, the register allocation table, performs register renaming. Register renaming, as the name implies, renames the registers, and this eliminates certain dependencies which allows more instructions to be executed in parallel. The Nehalem microarchitecture actually has 2 register allocation tables, since it can execute 2 threads in parallel. This block, the reorder buffer, is needed for speculative execution. Speculation means that an instruction can be executed before it is known that it should be executed. Finally, this block performs branch prediction. Branch prediction means that the branch direction and the branch target address are predicted based on the history of the branch and perhaps also on the history of other branches. Intel processors have very advanced branch predictors, and I will explain how they work. In the second course, I will also explain how you can accelerate your applications using so-called SIMD instructions. SIMD, or SIMD, stands for Single Instruction Multiple Data. These are instructions that process multiple data elements at the same time. In this example, 2 registers X and Y contain 4 data elements each, and the operation star is applied simultaneously to all elements by a single instruction. Many applications can be accelerated significantly by SIMD instructions, and therefore it is important that you know about them. Another objective for the second course is that you should be able to name and describe several core multithreading techniques. Core multithreading means that a single processing unit, or core as they are called nowadays, is able to execute several programs or threads at the same time. To provide a preview of this topic, this figure shows a part of the Nehalem microarchitecture. Highlighted in red are the retirement register file and the register allocation table. Notice that there are 2 of each. This is because each core is dual multithreaded or hyper-threaded, Intel likes to call it. To support it, Intel has duplicated the retirement register file and the register allocation tables, but the reorder buffer, the reservation stations, as well as the functional units are shared. The topic of the third course is Advanced Memory Hierarchy Design. After taking this course, you should be able to describe and apply several advanced cache optimization techniques. For example, this figure illustrates a technique called way prediction. This technique predicts the way of the next cache access. It attempts to combine the advantages of set associative and direct map caches, as I will explain in the third course. The fourth and final course covers multicore architectures. Modern desktop and server processors contain several cores and can execute several processes at the same time. For example, this figure shows a die photo of a processor with 4 cores with private level 1 and level 2 caches and a shared level 3 cache. In this course, I will discuss topics such as Snoopy cache coherence, distributed shared memory, atomic read modify write instructions, etc. This specialization is based on the textbook Computer Architecture, a Quantitative Approach by John Hennessy and David Patterson. You can either use the most recent edition, the 5th edition, or the 3rd edition. I'm not a big fan of the 4th edition. Sometimes the lessons will be based on other sources, such as research papers or other textbooks. I remark that although the specialization is based on this textbook, it can also be taken without the book. Nevertheless, it is a classic textbook in computer architecture that should be present on the desk of every computer architecture. Finally, let's enjoy the ride.